Good morning, Professor.
Good. I wasn't sure that I was at the right place, but I guess we're fine.
Yes, yes,
I guess Dr. Page can't participate today.
yes. I saw that just a few minutes, but okay. We can speak about these ideas of the Micopan Congress.
Very good. I sent you a file of my presentation. Well, I'm basically trying to augment your abstract and contribute to the paper. I guess you're writing a paper about the same topic. So I only have 3 pages. I can show you that right away if you like.
Yes, I saw this a few minutes, but I prefer you present this.
Okay, so let me share screen and we can start right away then.
Okay.
I'll try to, I think it's all set up right this time. I'm going to try to share here. Okay, can you see it?
Yes, I can see it now.
Okay, so that's your title, Local and Global Duality in Clifford Algebras. Clifford Algebras category. Okay, and I did put down the 3 authors, Jesus Cruz, Guzman, Garrett Sopcich, and Bill Page. Seminar developed in the paper developed in the seminar on fundamental problems in physics. So today's date. Okay, this is your abstract, so which I just copied from what you sent us.
Okay.
And so the material I'd like to add, somehow fit that in for your abstract is what I call the question, to answer the question, what is local and global duality in geometric algebra? So maybe I'll just read what I have here. The most familiar Clifford geometric algebra is the Clifford algebra of n-dimensional Euclidean space. In particular, of course, most well known is the Pauli algebra of 3-dimensional space, Clifford algebra of the Pauli algebra, but of course it generalizes to n-dimensional spaces. Okay, geometric algebras are usually defined in terms of quadratic form, or in terms of their isomorphic coordinate matrix algebra representations. They can also be defined as an ideal in the machinery of tensor analysis. Category theory, in turn, provides a powerful abstract framework that generalizes the concepts of tensor analysis through the idea of a monoidal category. I think that's correct. Whereas monoidal categories offer a flexible way of understanding these structures and operations, they lose the deep geometric insight into these structures provided in the framework of geometric algebras. Both the concepts of an n-dimensional Euclidean vector space and the corresponding dual n-dimensional covector space are incorporated into the concept of a globally dual basis of null vectors in a real 2 to the 2n dimensional geometric algebra of multivectors. Whereas global duality is a relationship between 2 to the n dimensional real Grossman algebras of null vectors embedded in a real geometric algebra of 2 to the 2n dimensions. Local duality is the Kronecker product or tensor product of a locally dual basis of null vectors in a single real geometric algebra of dimension 4, which is 2 to the 2, with a Lorentz matrix, fundamental to relativity and quantum mechanics. Okay, so I'm at the bottom of the page now.
Sorry.
The concepts of global and local duality are identical in the real geometric algebra G11 of neutral signature, algebraically isomorphic to the real coordinate matrix algebra of square 2 cross 2 matrices. The concept of global and local duality are also identical when the geometric algebras involved are taken over the complex numbers. Okay, so that's I think can be put largely into something like that can be put into your your abstract, and also your short discussion of what you want to present. And
yes, and I have some comments. I think that in the first part, I totally agree with the presented material. But when you arrive to the definition of local and global duality, I think that the viewpoints that I am working here is a different one, because I am in short, the idea is to speak about the global duality that you presented when you speak about the relation between two-dimensional real Grassmann algebras. I think that the same is in the idea that I am presenting in the paper, but this global duality is an approximation to duality.
Okay, let me just say this about what I'm trying to do. I think that with your category theory, what you're showing these relationships, that I am trying to show the same relationships by introducing a geometrical definition in terms of geometric algebras, essentially. So I think there is a deep relationship between what you're doing with category theory, but I think I'm covering basically the same ideas by introducing the idea of a locally or globally basis of null vectors in respective geometric algebras. I think I can, by the figures I'm going to present now to you, I think that this explains exactly the idea of what I mean by local duality of null vectors. Well, what we do, locally duality of null vectors is really the properties of a basis in the corresponding geometric algebra in which these ideas are being represented. And the same thing for global duality, which are usually represented in terms of tensor analysis, but which you are representing now using the much more sophisticated category theory. That's my, and I think I've been able to clarify the relationship of global duality in terms of a relationship between two Grassmann algebras on one hand, and local duality is regarding the tensor, either the tensor product of let's see, what did I say exactly? How did I word that? Yeah, the Kronecker product or tensor product of a
Right.
locally dual basis of null vectors in a single real dimensional geometric algebra of 4 dimensions with the Lorentz metric. But global duality is actually a relationship between 2 Grossman algebras of null vectors embedded in the real geometric algebra of 2 to the 2n. So that's of course what I'm expressing in this figure, a universal algebra of null vectors, and that's the last figure. So as far as local duality, we express in terms of a locally dual basis defined by 2 vectors, just 2 vectors, C1 and C2. Well, it's spanned by 1, C1, C2, and C1 wedge C2. It's a real geometric algebra. And with the simple multiplication table, choosing A equal to C1 and B equal to C2 gives a dual 2-dimensional Grossman algebra with the following multiplication table. Of course, that's where it goes beyond by expressing these 2-dimensional Grossman algebras in terms of the tensor product of the simple locally dual null vectors C1 and C2. That have this very simple multiplication table. So that's the locally dual multiplication table of a simple geometric algebra defined by C1 and C2. Now, I relate that in this picture. This is the geometric interpretation. When we get the standard basis of the geometric algebra, which I've talked about before, of course, in our seminar. I define F equal to A minus B and E equal to A plus B, and you'll find very simply using this multiplication table that E and F are anti-commutative and have F squared is equal to -1 and E squared is equal to +1. Okay, and then this final graph here, of course, that's where I go up. So A and B are the Grossman algebras, and the Clifford algebras they induce is a Clifford algebra of neutral signature n comma n. Now we've talked about those ideas before, but so I'm making a clear distinction when I talk about global duality. We're using a geometric algebra of neutral signature to incorporate both vectors and covectors, which are, of course, expressed in tensor analysis, and also which you are expressing in your category theory treatment of it. Now, but on the local duality, which I think is missing, that's what I hope that you can express in terms of, we know how to express it in terms of tensor analysis, but regarding this structure of a monoidal category, how is it best expressed? I think you express the equivalent of what I call global duality, which is the same thing in geometric algebra. That's the relationship between 2 Grossman algebras expressed in a geometric algebra, which has, well, I express it, let's see, in this final figure here. So given the globally dual null vectors of the Grossman algebras generated by the vectors AI and BJ, which satisfy this inner product in the geometric algebra of neutral signature. So you can see, when I look at local duality, it's really the tensor product in the more general case of 1 comma n and n comma 1, then this picture applies. But if we complexify those algebras, then we have exactly the same structure. So we lose the distinction between global duality and local duality when we complexify those geometric algebras. And that's really involves the classification of all geometric algebras fall in this scheme. They can either be classified in terms of two globally related Grossman algebras, which gives a Clifford algebra of neutral signature, or in terms of the Kronecker or tensor product of one simple locally dual bases, C1 and C2. Now, notice that when I go from, in this table here, I define A equal to C1 and B equal to C2. But when I go to higher dimensions, then we get this structure here. We have two Grossman algebras, this one of 2 to the n dimensions, and this Grossman algebra also of 2 to the n dimensions, which when we impose that neutral metric, we're able to incorporate both duality and covectors and vectors into the same geometric algebra, which are globally duality. Now, local duality, we're really taking the Kronecker product of a single simple geometric algebra, namely the real isomorphic to the real 2x2 matrix algebra.
Where is the Kronecker product in the figure in
this in this picture right here.
This picture, yes.
So that's right. So that's what I try to explain in the note here. The local duality, the locally dual geometric algebra. Okay, is a simple geometric algebra generated by C1 and C2. But in the general case, then we're looking at geometric algebras of 1, n generated by C1 up to Cn plus 1, which satisfy this duality condition. That's the local duality condition imposed on these null vectors from the simple geometric algebra generated in this picture right here, C1 and C2. Now the idea is you can expand that to any numbers of C's in a locally dual basis, which is the Kronecker product of G11 with itself n times to get to square the dimensions that we need. We can define isomorphisms between these two algebraic structures, real geometric algebra structures, or if we complexify it, then we get exactly the same thing. So that's what I'm saying. I think that's basically what you're saying in your microfam paper that you sent us the abstract on. But what's missing, I think, is a clear definition, which I hope that you can include in your final paper. I think it is. I think I've clarified the ideas by talking about, okay, so global duality is where we take two Grossman algebras of 2 to the n dimensions in the general case, and we define the product by this simple relationship. Let's see, where is it? Okay, so that's in the general case. The globally dual null vectors of Grossman algebras are generated by two Grossman algebras generated by AI, A1 up to AN, and B1 up to BN, satisfying AI dot BJ is equal to 1/2 delta IJ. And of course, when I is equal to J, then that just says that AI dot BI is equal to 1/2. And that's the generalization of the simple case of two vectors, C1 and C2, because instead of choosing A and B equal to C1 and C2, we can choose AI and BI equal to CI plus CJ and BJ equal to, and those are the algebras that we're taking the tensor product of them. And I think that's what I've been missing in my presentations to our seminar, which both you and Bill have called my attention to, and which I have finally now, with this 3 pages, can explain clearly. I hope that we can talk about it more, but that's basically, by introducing these pictures, I hope that clarifies the geometrical aspects of what you are doing with a much more general structure of a monoidal category, which I do not completely understand. But I believe that That's what you are talking about, monoidal categories in your paper, are you not? In your
Yes, yes, and here I like to understand the idea in correct way, and then I think that this can be included without a problem. But I don't understand some parts of your proposal, because I like to.
Well, of course, I can expand it more, but as far as today is concerned, I could only do it very generally in terms of these pictures that I've drawn.
Maybe you can't understand my question if I can write something in here in the screen.
Okay,
Maybe
well, that's fine. That's fine. Whatever. Basically, that's all I have to say. Well, I hope I can help you better understand exactly what I'm saying with these two, by these two pictures. Well, like I say, the right side is really the Kronecker product or the tensor product of the simple four-dimensional matrix. So you can think about it as a Kronecker product or the tensor product of those 2x2 matrices, real 2x2 matrices. But if you complexify it all, then local duality and global duality correspond to the same geometric algebra. There's only one geometric algebra over the complex numbers. Now, what happens in the case of when you use the complex numbers, the category, a monoidal category over the complex numbers? What happens when you take your scalar field to be the complex numbers? It should reduce to your definitions of duality, of local and global duality, if I understand it correctly, should introduce to one concept of duality in the monoidal category. Is that true or not?
Maybe I can annotate something. I don't know how we can share the screen here for
double share or something. I can split the screen with you, maybe. I can reduce the size of mine, and maybe there's room for you to.
No, but maybe I'm going to change something here.
Okay, you can write on my slide if you want, of course.
Wait
I
a
don't know
moment.
if can you write on my slide? I'll leave it up for you there.
I need to find my file. A moment, please. I think that our ideas are going close, but I need to express in the context of the
category theory, monoidal category
theory.
How these ideas correspond to each other.
Yes, and then for this, I like to understand in a correct way all the
how these. Yeah, that's exactly what I have to do in your paper that you're writing. I can also clarify these ideas by actually giving you the tensor product, or I can give you the tensor product or the Kronecker product definitions of these CIs, which is what I'm not talking about here.
Yes, yes. This is fundamental for this. But wait a moment, I think this.
Yeah, I guess they don't allow graphs in an abstract, so that's I think you can take from what I wrote above here, in this discussion, you can use some of this in your abstract. You can say something about what I've wrote down here. I think would fit into your abstract nicely, but I'm not sure exactly how you want to do that. But this basic discussion here would be for the abstract, or parts of it, or part of it, trying to understand how a monoidal category is related to, in a geometric way, when you introduce a geometric algebra on a globally or locally dual basis of null vectors. That's where the idea of global and local duality arises, when you introduce a locally or globally dual set of basis vectors which satisfy either just A1 dot B1 is equal to 1/2 delta, well, equal to 1/2, that's in the simplest case. Or if you generalize that, then you get two Grossman algebras of 2 to the n dimensions each, where you introduce this neutral geometric product, the neutral signature, which corresponds to Gn comma n. Okay, but that's a global duality. But the local duality becomes taking the Kronecker product of these simple geometric algebras generated by C1 and C2 with the inner product C1 dot C2 is just equal to 1/2. Well, it's equal to 1/2 1 minus delta ij. That means, of course, if I and j are both equal to 1, then that's 0 because they're null vectors. That's why I'm using those. That's why I think that this universal algebra of null vectors is what's missing in mathematics, basically. They don't look upon it as going up. But that's what I think is very important, and which you can nicely express in terms of monodal categories. But I think we're talking, well, that's the thing. That's what we have to, but that would be in the paper, not in the abstract. So I think in the abstract, you can incorporate some of the material I put down here, just a very simple, expand your abstract to include this or something.
I have here some more ideas about this. And here first I define the algebra category. Then it is important this definition because
do you want to share your screen? I'll just cut mine out. I can stop sharing my screen.
Okay. Then
you do have my paper that I sent you. Maybe you can look at. I did send you the paper, so I don't really have to keep it on the screen. You can look at the paper of the last picture or whatever.
Yes, I don't know if you are seeing my screen now.
You want to share it, or it is shared? I can reduce my screen. Okay, maybe you're. Okay, I don't see what you've shared, so I can end my share.
I think that now I am sharing my screen, but I think that you are seeing your paper and not.
I'm going to end my sharing. Okay, let's see. How do I? Maybe I just have to. Oh, stop share. There it is. Okay.
No, you are seeing now my screen. Look at this. This is my screen.
Oh, okay, good. I see it now.
And then now I am putting the draft paper that I am working. This is the abstract, and the title is this. But the important things are that I have starting here with a definition
of a graded module. That I think that's very important. So instead of using a graded module, I use a graded Grossman algebra. Well, that's a module too. So that's just a different language. We're talking exactly about the same thing.
Okay, but then I am presenting here in a categorical language the definition of an algebra. Then this is an algebra category. And we have to, and this is an important thing, we have here to here we have two kind of morphemes that are homomorphisms in the category. One of
Okay.
it takes to us from the from the field to the algebra, and the other one define the properties of the product. Then this is a very general definition, but
okay.
But now we introduce here the idea of grades, and I start with, I am going to change the color, and then we start with the idea of graded modules. And the principal idea about the graded modules is that if we can split the modules in terms of incomposable modules, then we can speak about grades. Then
okay, I think that's what I'm talking about when I split it into the Kronecker product of these simple geometric algebras G11. That's exactly M1, M2 corresponds to my splitting with the locally dual basis. Now, if you complexify that, I think that will go into just exactly the same as the global and local become the same. So a graded module, that's where I think corresponds to my two Grossman algebras. So okay. M1 and M2 are two graded Grossman algebras of null vectors. That's how I would translate your graded modules.
Okay, and then the idea is that first to start with graded.
Okay, and then when you write M as the sum of this thing, that's where you're talking about the local duality, equivalent to my local duality.
Wait a moment.
Okay.
I go back here and I go more more around this, because how you can see one idea for the grades is to split a module in terms of discomposable modules, like a direct sum. But the another idea is to split the module in terms of a complex. Then
over the complex numbers you're talking about?
No, a complex is a relation.
A complex.
Between
complex of modules. Okay.
Between modules of different degree.
Okay.
Here, I plus 1 is the degree of this module.
Okay.
And then we can go over this. But then we have here in this complex of modules, we have the possibility of build a duality. And then in each of these identicomposable modules, I can build a duality too. Then when I build the duality here, it is local duality. But when I build the duality here, this is global duality.
Okay, I think this is very interesting because I think your category approach is really saying that any geometric algebra of any signature can be split into arbitrary dimensions. That's your writing here, a sum of arbitrary dimensions.
Yes.
So what you're doing is even more general than what I'm only presenting the case of a particular class of two geometric algebras, either a geometric algebra of neutral signature. Those are geometric algebras of the form n comma n, or local signature, where you're just taking small geometric algebras of 2x2 equivalent to 2x2 matrix algebra, or a Clifford algebra generated by a neutral signature 1 comma 1. But for the dimension 1 of 2, real dimension of 2, those ideas correspond. They also correspond is when you complexify the pieces, no matter what their dimension. If you complexify the whole thing over the complex numbers, then it reduces to a single module m over the complex numbers. So I think our ideas are very close, except in category theory, you're able to tear it apart to generalize to any Clifford algebra. And I could do that as well, but I've tried to keep it simple to try to understand just in the most simple case, which is the case of local duality and global duality.
Yes, this is the idea. Taking this general idea, go to the simple case, and then we can work with this. Okay, here there are some definition of functors that maybe in this moment are not important. And this idea of triangulated category is important for building the duality in the complex module, but not yet for our discussion.
But by the way, when do you have to have the final version of your paper? When do you have to have that? When you're writing a paper about these ideas, which you'll publish, I suppose, with the conference, the conference. When is the paper? When is the date that you have to have the paper in its final form?
I think that it is the final of August this month.
Mm-hmm. Oh, okay. Well, that's a challenge then to finish it by then.
No, in fact, they accepted my extended abstract like a contribution for the proceedings of the Congress. Then, in fact, we can stop for this, but after we can send a more detailed paper for publishing in
somewhere else. Somewhere else,
in an specialized review.
Okay, well, like I say, I think what you're doing with your category theory is more general, and really, that in the more general paper, then we would explain exactly how using Clifford algebras is just a way of covering basically the same material. A Clifford algebra of any signature is expressing those ideas in category theory. That seems to be.
And then here is the general ideas of
A monoidal category.
algebras. Here is the idea of monoidal category.
Okay, very important for me to understand that better.
And then after of this, here is an important definition about duality.
Okay.
Here it is.
Oh, okay.
Then we speak here about the dual of an object using the home set associated to the category lambda. Then here we use an object that is a module, and then the home set related that make the relation between the module and the identity element in the category that, for example, are the reals or the complex or the scalar fields, for example, in a more general view. And then we can build here the dual for that category. And then with this idea, we can go to the here.
Okay. Okay. Perfect. Perfect.
Of Clifford algebra.
Okay. Very
Then
good. That's what I'm basically saying about that. I think, yeah. Okay. Very good. So that's I'm talking about a special case of that, but you're taking any Clifford algebra. So okay. I'm
yes.
only taking, okay. I'm taking a subalgebra. I'm taking Clifford algebras which have signature a Lorentz metric or a neutral metric, whereas you're taking any Clifford algebra. So that's great. I think it's a great paper.
Then here we start reviewing the general definition of a Clifford algebra. And then when we put in terms of category, then we are going to define the Clifford product.
Okay.
And then with this idea, and because of this, we speak before about the tensor categories here in the previous section, algebras in tensor categories. And I need to put more ideas here, but this is too much important because first we define some properties of the tensor algebras in tensor categories or tensor algebras, and then we use this for define the Clifford product. Huh?
Okay. But you can see this is very abstract idea. A Clifford algebra itself is a much simpler structure than all this category theory you're introducing to talk about it.
And then here we have two different products.
Okay.
Symmetric product.
Okay.
Where this is important because this is built in the expanded in the ideal the um, of the vector space that is expanded with the tensor product of this space without the antisymmetric part.
Exactly.
This is the idea here. And the other one is the exterior product. And then the exterior product is the...
Okay, you're introducing that as an ideal in a tensor algebra as well, I suppose.
Yes, this is the idea, and the introducing ideals in tensor algebras. And then with these two definitions, the Clifford product can be defined in this way.
Okay, but you can see how I'm going. I'm going exactly in the opposite direction. I'm starting with a Clifford algebra and showing how I think you can go exactly the other way and show how that defines a category and a monodal category, going the opposite direction. That's what we.
Yes.
So but that's the thing. The Clifford algebra is a geometric, completely with a geometric interpretation of all the elements. The category theory, you're putting everything in terms of algebra. So I guess you can say that's the algebrization of Clifford algebra. Category theory, monodal category theory is just pure algebra, really. Properties of algebras, homomorphisms between algebras, and all these other structures you can define between algebras, which you also define in terms of your category, a monodal category.
Yes, and now here, when we have completed the general definition of algebra, we can go to the elements of the algebra.
Okay.
And when we go to the elements of the algebra, we have two ways of definition of this algebra. One in terms of nilpotence, that is here. And,
okay.
And
now you're getting close to my to what I call universal algebra of nilpotence.
Yes, and one in terms of idempotence.
Okay.
That I have not put it here yet, but the idea is to put these two definitions of Clifford algebra. And here I have this idea of how to show that the definition of Clifford algebras in terms of idempotence can be transformed in the Clifford algebra in terms of nilpotence. Then there are a general property of the ideals of a module and the ideal of the I forgot the term, the idea of the complementary part of this module that is taken with the nilpotence. Then,
yeah. So if you remember when you introduced these locally dual bases of null vectors, if you take the product of any two of them, Ci times Cj, that is an idempotent. So any idempotent can be, any primitive idempotent can be represented as a product of two nilpotents. And that's where the idempotent comes in. Well, two nilpotents which have the inner product of C1 dot C2 is equal to 1/2, or CI dot CJ is equal to 1/2. C1 times C2 defines an idempotent constructed with the two locally dual null vectors C1 and C2, or more generally CI and CJ. I think that's exactly what you're saying.
Yes, yes, because we can put the product in terms of idempotence in terms of nilpotence.
Perfect.
But then, and then I arrived to this idea. The concept of duality is the same in both.
Okay.
Expressions.
Oh, okay. Okay.
Uh-huh.
Yeah, but you're putting covectors and vectors into the same space, basically.
No,
Well,
because
that's the way I'm doing it with geometric algebra. I'm putting vectors and covectors into the same space and giving them an algebraic structure. So in that case, C1 squared is equal to 0, equal to C2 squared equal to 0, and C1 times C2 is an idempotent.
yes, but you can see here that then we cannot use properly vector and covector here because instead of this, I am in
Yeah, because we're using local duality, and that's more general than just covector and vector.
No, because we are now in the vector space, and when we use idempotence, we have a base for this vector space. We build a base for this vector space, and when we use the nilpotent, we are in the complementary base of the same
Okay, that's fine.
of the same vector space.
Okay.
And then in Clifford algebra, vector space is self-dual.
What was that again?
Self-dual. Because the vector space is self-dual, because the dual of the vector space is the same that the vector space.
Okay.
Only with different bases.
Okay. Yeah, that's fine. Yeah, but that's the same thing as taking the tensor product of
No.
Well, I believe it is.
No.
Well, in the simpler case, like I say, my case is only much more with a Clifford algebra of neutral signature n comma n, or a Clifford algebra of signature 1 comma n. Now, the more general Clifford algebras, what you're talking about, is p comma q, and I have to do more work to get. So that's what I would ask you. How would you take just two Clifford algebras? Take the Clifford algebra, two types of Clifford algebra. The Clifford algebra generated by a metric of neutral signature, which means that you have, in the standard basis, you have A1, A2 up to AN plus AN. They're all null vectors. And B1, B2, that's the two Grossman algebras. Okay, that's a special case of what you're doing. So that's what I'd like to understand. If you look at the special case, not all Clifford algebras, but just the special case of a Clifford algebra of signature, neutral signature, which is n comma n, or this Lorentz signature or Minkowski signature of 1 comma n. Those are just look at those two Clifford algebras. Then I think that I have a translation in terms of a tensor product of the simple Clifford algebras C comma C11, or a Kronecker product of those algebras. I can give those definitions simply.
No,
But for a general Clifford algebra, then okay, then you can use your theory that you have. But I want to narrow your discussion down to classes of Clifford algebras of the form of neutral metric n comma n, or of metric 1 comma n, or n comma 1 of a Lorentz metric.
No, I am speaking in a different way because here I am supposing that I have two different spaces for the Clifford algebra.
Oh, okay. Well,
in the first, we have the condition EIJ equal IJ. Mm-hmm.
Okay.
Mm-hmm.
So that's Euclidean. That's Euclidean, basically.
This, yes, that's
Euclidean Clifford algebra.
And yes, and here in EIJ, we have different, because this is 1 minus IJ.
Okay.
Then the first are idempotents. The second are nilpotents. Mm-hmm.
Okay, well, let's see here.
Yeah,
so what is E? Okay, okay, 1, but okay, you don't have a 1/2. The only difference between your definition and mine is I put a 1/2 in front of the.
Okay, you want to put here Q.
Okay, Q.
In more general way.
Oh, okay, that's fine. That's fine.
Okay, and then here.
Now Q could also be negative, of course. That's different, of course, but we'll keep it Q positive right now.
Okay, and then you want to okay, yeah, I need to change the signal in the definition. Okay, here it's
okay. It could be plus or minus then, whatever.
Plus or minus. Okay. Then and then with this.
Okay, so given that, what Clifford algebra is that? What Clifford algebra does that relationship define?
Sorry?
What Clifford algebra does this relationship E parentheses I, E parentheses J equal to plus or minus Q times 1 minus delta IJ? What Clifford algebra is that defined by that relationship?
Whatever Clifford algebra you want. Either this Clifford algebra can.
Okay, but yeah, it's defined totally in terms of null vectors. Is that correct?
The first is in terms of idempotents, and the second is in terms of
okay.
vectors.
Yeah, okay, but you see, what I do is I put those ideas together in one. Yeah, it's just a little different, but it's obviously very closely related that we're talking about.
And here is I is the product of E1 E2 without
up to EN or whatever, EQ or EQ or whatever.
Without EI.
Okay. Oh, okay.
No.
Okay. So now you're going back to the top line then, right?
Yes. yes, and then this is the definition, and this is a blade in the Clifford algebra. Mhm. And in this blade, we can build the base of this Clifford algebra. Then, with this idea, we can find different kinds of representation of the Clifford algebras that are duals. Here, this is the dual is the dual
okay.
of the first. Then I have here the definition of duality. But if with this different decomposition, we can build different kinds of dualities. Because in a more detailed way, we can have EI, EI, EJ, EI, EJ, EK, etc. And then with this, sorry, first I need to put 1.
Okay.
Uh-huh.
Okay, well, like I say, you're doing all this in a monoidal category. That we're really talking about monoidal categories in all of this, what you're presenting, I suppose.
Yes. Uh-huh.
Okay, so that's right. By introducing the idea of a monoidal category, you're able to characterize any Clifford algebra.
Any Clifford algebra.
Okay. Well, I'm able to characterize any Clifford algebra by introducing either two Grossman algebras that are globally related, in the sense that if they're globally related, then they characterize a Clifford algebra of neutral signature. If they're locally related, they categorize a Clifford algebra of Minkowski signature. Now, if you have any other Clifford algebras, it's the tensor product or Kronecker product of these various, of either the Lorentz case or the Grossman algebra case.
But you can see that when I speak about this Clifford algebra, this is the dual of this.
Okay, so
this the dual.
EI squared is equal to 1. Is that correct? And EI
parenthesis is
squared is equal to -1, right?
Yes. Mm-hmm.
Okay, well, that's exactly what I'm doing.
No equal to -1. This is equal to 0.
Oh, those are null vectors then.
Yes. I got to null vectors here.
Oh. Well, that's a little different than what I'm doing, but that's fine. We can better understand exactly what the relationship is, but we're really talking about the same thing, I believe. But when you introduce category theory, well, that's what you do. In the language of category theory, you introduce a monoidal category And then you see how Clifford algebra is related in a monoidal category. But I'm seeing how any Clifford algebra is related in a tensor product of simpler geometry, either locally dual, corresponding locally dual Clifford algebras, or globally dual. And that's the two ideas you're talking about, the extreme cases. That's why I would like to see if you just how your ideas would translate directly into what I call local duality of a set of null vectors, or global duality of a set of null vectors. And that's where you're changing. You have a different idea. You say that the E parentheses I is a null vector. Well, for me, no, yeah, it's just a different way of getting. I believe we're still talking about the structure of a general Clifford algebra, but I haven't finished mine yet.
But you can see that I put better here with this. You can see that this is the dual.
Oh, okay. But the EIs are null vectors. That's strange.
This is
Whereas EI squared is equal to 1, EI parentheses squared is equal to 0. Is that I think I understand that correctly. You're saying that E parentheses I squared is equal to 0. And then
yes.
you're defining. Okay, well, that's different than what I'm doing. Because I'm starting with all null vector structures and constructing everything in terms of that. And we're a product of any, in the local duality case, a product of any two of them is an idempotent.
But
C1, C100 times C200 is equal to an idempotent, but C100 squared is equal to 0, and C200 squared is equal to 0.
yes,
it doesn't matter. Yeah.
But the idea is that here I can build a subalgebra. Here there is another one. And so
I wish that Zbyszko were still alive. Maybe, I've talked about these ideas with Zbyszko too, but I think we're closer to getting an understanding of how our ideas are related than I ever got with Dr. Ozhevich. We're closer to understanding. Well, that's right. He got very interested in category theory. And of course, he basically taught you category theory. And now, I'm trying to understand what I tried to explain to Zbyszek. Well, now you're explaining in terms of a monoidal category. Did Zbyszek do much with monoidal categories or not? Did Zbyszko use theory of monoidal categories when he discussed Clifford algebra?
Yes, I need to think more about this because I have not here a subalgebra.
Okay, well, I think the important thing is that to get at the idea of a Clifford algebra using category theory, you have to introduce the idea of a monoidal category, and that forces you to look at it in a certain way. But with my idea, I start with either a pair of Grossman algebras, two to the n-dimensional Grossman algebras, which have a relationship between them, which defines a Clifford algebra of neutral signature, or my other construction is are Clifford algebras of Lorentz metric, which are defined by a locally dual set of null vectors, which have, and I think it's just you're introducing monoidal categories to get at the structure of a Clifford algebra, whereas I'm more directly, I think much more simply, introducing the structure of a globally set of dual set of basis vectors or a locally, and taking the Kronecker, either the Kronecker product of those algebras or the tensor product of those Clifford algebras to generate the more general structure. So it's, I just don't have to use a language of category, a monomial category. So,
for example, if we speak about the Clifford algebra, CL3, what are the subalgebras of this algebra?
well, yeah, CL3 can be considered to be CL11 over the complex numbers. That gives you the structure of CL3. So that's the interesting thing. What happens if you take everything you've talked about so far is over the real numbers? But what happens if you take it all over the complex numbers? And then I say those ideas collapse into one structure.
But then one is the CL12, and then the other one is CL21.
That's right. Yeah, CL3 and CL12 are isomorphic. Algebraically, they're isomorphic. You just change the definition of what you mean by a bivector or a vector into properties of anti-commutativity. But CL21 is different. No, that's different. That's not isomorphic to CL12. But if you take everything over the complex numbers, then they're all isomorphic to C11 complexified. So C12 and C21 are isomorphic to CL1, 1 over the complex numbers.
To see L1, 1 over the complex numbers.
Yeah, you take CL11 over the complex numbers, in which case all those are indistinguishable. They're all isomorphic.
But if you stay in the same field.
Well, that's right. Then if you take only the same field, say the real numbers, then CL21 is not isomorphic to C21. But CL3 is algebraically isomorphic to CL1, 2. But what's different is what you call a vector and a bivector. In the algebra, CL12 is different than what you call it in CL3.
CL3 can be split like, this is a question. Like CL12 plus CL21.
Well, but what would be the dimension if you over the dimensions are not the same on that. CL3 is not the same dimension as CL1. That plus, what does that plus mean? CL21. Well, yeah, that's not. I don't know. The dimensions are different there. I don't.
We need here not, but okay. Yes, the dimension not, and then.
Okay, what I'm claiming is that CL3 is algebraically isomorphic to CL12, but it's not algebraically isomorphic to CL21.
Okay, but here.
But if you take CL1, 1 over the complex numbers, then all three CL3 is isomorphic to CL11, is isomorphic to over the complex. They all collapse into the same structure. If you take CL11 over the complex numbers, the Clifford algebra reduced to a complex Clifford, three-dimensional Clifford. Let's see. They all have the same dimension of C. It's just the Clifford algebra CL3. CL3 is isomorphic to 2 cross 2 matrices over the complex numbers. Okay, CL3 is isomorphic to 2 by 2 matrices over the complex numbers. So is CL12, and so is the Clifford algebra CL21. Isomorphic to matrices over the 2 by 2 matrices over the complex numbers.
Okay.
I think I got that right. But that's
Okay.
the thing, and that's of course what I'm trying to point out in that final picture. That's what I'm trying to draw in that final picture of the paper that I sent you, the local, which what I sent you.
Yes, and I think
You see, if you look at the paper, if you can look at the slide, you'll see that CL2N over 2 to the NC,
maybe I can
that's a matrix geometric algebra, and that's the same thing. They become the same thing. Well, wait a minute. No, it's not quite right. Oh, well, that's different there. Yeah.
No, I can.
Yeah, that's a little different. That's on the left side then of that. Let's see here. That was, yeah. So this last table I give you, the last figure on that page 3 is exactly what we'd have to translate to see how exactly that's related to your category theory of any geometric algebra will fit in my figure 3. So, okay, you're saying any geometric algebra will fit in your category theory with a monodal, in terms of a monodal category. So I claim any Clifford algebra can be reduced to, can be fit into this diagram, but really I'm only looking at the special cases here. So that's the thing. The classification of all Clifford algebras you're really talking about in terms of a monodal category. But of course, there's many ideas you can talk about isomorphism, algebraically isomorphic Clifford algebras. They introduce, well, that's just like the information in a monodal category. You're introducing all kinds of additional structures in order to talk about the structures of any Clifford algebra. Well, anyway.
Okay.
So we have a lot of work to do. Well, I think you can add something from the first page of my what I've sent you into your abstract, just to try to clarify a little bit what we're talking about, or what my local and global. Maybe they're not exactly the same concepts of which you're using as local and global duality, but since you're listing me as a co-author of your paper, you should make a distinction of what I'm calling local and global duality than what you're showing in your category theory. So I think you should add something to your abstract because, well, you're putting me down as a co-author, but actually our definition of local and global duality are different. So somehow, but I think they really can be explained together, I believe.
Yes. I think that we arrived at an important point, because we are now trying to put in a concrete way this.
Well, I think you are clarifying the arguments that Dr. Ojevich and I had over, 30 years ago. So the fact that he stayed at FESC and I went to UTLA is the reason why I was developed my idea. If I stayed at FESC, Spishak would overwhelm me with his ideas. Maybe I would be talking about category theory just as you are, but monodal categories, I would be talking about monodal, which the work you've done, you figured out what I didn't understand. But I don't even know whether Spishak understood, because he could not relate our ideas. You're actually doing something new in this paper of local and global duality and Clifford algebras. You're explaining those ideas. Zbyszek never did that in a monodal category, to my knowledge. You know what Zbyszek did, I don't.
I don't remember about that.
But he did teach you category theory. I tried to, I was teaching you Clifford algebra. And you've put the ideas together in your monodal, in a monodal category. That's the way I understand it. But you should bring that out at least in your abstract. I hope we could amplify these ideas and show more precisely. They must be related in a monodal category. That's the key idea.
Yes. Yes. I think that I can work in that, and then maybe we can continue working in the idea of put in one.
In your final paper due at the end of August, well, I can help you with that, clarify these ideas.
Yes.
And include these figures. I think these figures are instrumental in understanding what you're doing with a monodal category. But mine isn't completely general. Yours is more general, I admit that. Mine only apply to two, as I describe it here, only to apply to two types of Clifford algebras. Namely, those with a Minkowski signature or those with a neutral. That's where you have two relationship between two Grassmann algebras, two to the n Grassmann algebras, where P plus Q is equal to n. So, yeah, that's right. So I would, for a general Clifford algebra of signature P comma Q, I would say n is equal to n plus Q. And then define the structures involved in the global case and the, anyway, I think we can do that. It shouldn't be too hard, just on the basis of what we talked about today now. But so the only thing for your abstract, I would try to include something to distinguish between what we're saying, the two definitions of local and global duality, which are different, which because of the structure of a category, a monodal category, which I don't fully understand. So.
Okay. Okay.
Well,
yeah.
So I don't have much more to say. Maybe we could end the. I guess
Okay.
it's been what, an hour and a half now. So
Yes, and then maybe we can wait about the comments for Professor Reich.
Exactly. Yeah, it's too bad that he was able to come and join us today.
Yes. Okay. Okay. Nice to.
Oh, it would be nice if you had an extra week. Do you really have to turn it in at the end of 2 weeks? At the end of August, maybe they could push it to give you a little more time on that, on your final. Could ask for it.
I think maybe we can add more, and I am going to add some of your ideas in the abstract, the extended abstract that I sent, and I think that we can send this in like it is.
Okay.
Like now.
Okay.
And then we can continue working for the final version of the paper.
I think Dr. Ojevich would be very happy with what we're trying to do.
Yeah.
And I would be very happy too. I'm just sorry that he can't join us. He would probably be able to help us both out.
Yeah. Okay. Well, then we can see in 3 weeks.
Okay, perfect. I've enjoyed it very much talking. I'm just sorry that that Dr. Page could not join us today too.
Yes.
But I'm sure he'll have some ideas that he wants to tell us about next time too.
Okay. Bye.
Okay, so have a nice day. Have a nice 3 weeks.
Okay. Bye.
Okay, take care. Nos vemos
No.
pronto. Adios.
Yes.